This video is about pressure. We'll start out with a definition here. Pressure is defined as force over an area, force applied over an area, F over A. If we look at the units of force, well, force is mass times acceleration, and the units of mass in the SI units would be kilograms, acceleration would be meters per second squared. So if we plug those in, we get 1 Newton. 1 Newton is 1 kilogram meter per second squared, and Newton is a unit of force. So if we take the SI unit of force, newtons, divided by the area in meters squared, we get a Pascal, unit of pressure. 1 Pascal is defined as being 1 Newton per meter squared. And if we look at the units, we break this down, take newtons and make it kilograms meters over second squared and meters squared on the bottom. It ends up that the units end up as kilograms over meters second squared. Those are the units of Pascals. So 1 Pascal is 1 kilogram per meter second squared. This is a good relationship to remember. It helps explain some things. Here are some relationships, some conversion factors between various units of pressure. Atmospheres on the left. The way I have this set up is atmospheres, 1 atmosphere, exactly 1 atmosphere is on the left, and what it's equal to is on the right. So this is a conversion factor. It's equal to 101,325 pascals, which is 101.325 kilopascals. 1 atmosphere is equal to 760 millimeters of mercury. Mm is millimeters, Hg is mercury, which is the same as 760 torr. 1 atmosphere is also equal to 1.01325 bar and 14.70 psi, or pounds per square inch, and 29.92 inches of mercury. In is inches, Hg is a symbol for mercury. The ones with the asterisks, the green asterisks, these are exact numbers. The ones that don't have asterisks are not exact. So if we look at this barometer here, this is a simple barometer, and the way this is set up is we have a column, a glass column that's closed at one end up here, and down here you can't see it, but it's open. And we start out with a vacuum, nothing in here. Then we invert it, put it in this pool of mercury. This is mercury down here in this bowl, and we let it go. What happens is the atmosphere will exert a pressure on the surface of this pool of mercury, and because there's nothing at first, there's nothing pushing back down here at the base of the column of mercury, the mercury gets pushed up into the column. But as it goes higher and higher, gravity is pulling the mercury down. It's accelerating it down towards the center of the earth. And the higher this column of mercury goes, the greater the pressure it exerts at the base of its column. And you reach a point where the pressure exerted by the column of mercury exactly balances the pressure of the atmosphere. At that point it stops moving, which means that the height of a column of mercury in this setup here is a measure of pressure. So we can calculate the pressure at the base of a column of liquid with this equation here. Pressure is equal to dGh, where d is the density of the liquid, g is the acceleration due to gravity, this number right here, at least to 6 sig figs, and h is the height of the column. So remember this. Now this is another way of measuring the pressure of a gas, and this is what's called a manometer. This is an open tube manometer because it's open to the atmosphere up here. So what's going on here is you have a gas in this sphere here, and probably it came from a chemical reaction that happened in here. Now this is a curved glass column that's hollow inside, and there's mercury in here. Now does it make sense that if the pressure inside of here was the same as atmospheric pressure, the height of the column of mercury would be the same on both sides of this U right here, right? Because this pressure would exactly balance this pressure, and if they're the same, then it's the same height. But if the pressure inside of this flask is less than the atmospheric pressure, the atmosphere is going to push this side down and up over here, and so we can say that the pressure inside of the flask will be equal to the atmospheric pressure minus this height right here. Because remember, the height of a column of mercury is a unit of pressure. On the other hand, if the pressure in here is greater than atmospheric pressure, the gas in here will push this column of mercury down farther on this side, And so the pressure of the gas inside here will be equal to the atmospheric pressure plus the height, the difference between here and here. We can do a couple of examples. Let's calculate the pressure in atmosphere. An atmosphere is exerted at the base of a column of mercury, and that mercury, when it's in equilibrium with the atmosphere, is 1.423 meters high. And I give you the density of mercury at least to 6 sig figs. So we're going to use this equation right here. But first, we have to get our units right. Remember, SI units, okay, to get pascals, which is what we're going to get here, we have kilograms meters over second squared. Well, our density is in grams over centimeters cubed. So the first thing we're going to have to do is convert the kilograms over meters cubed. And so we do this right here. We know there's 100 centimeters in a meter, and we cube both these. Units of centimeters cubed cancel. We get meters cubed on the bottom, and then this is just converting grams to kilograms. And it ends up that it's 13,595.1 kilograms per meters cubed. That's the density in these units right here. We have G, which is also already in the right units, and H, the height, is already in the right units. So we plug it into the equation. Pressure is equal to dGH. This here will limit our sig figs, 4 sig figs. It ends up we get 1.897 times 10 to the 5th, and it's kilograms over meters second squared, which remember are pascals. But we want this in atmosphere, so we still have to convert it. So all we do is use one of those conversions that I showed you a minute ago. Convert pascals to atmospheres by dividing by 101,325, and we get 1.872 atmospheres as our answer. Let's do another example. And this is interesting. Let's figure out what height in meters we'd need to have a water barometer if we used water instead of mercury. And let's see how high that water barometer would rise if the atmospheric pressure was a reasonable pressure, 764.2 millimeters of mercury. Remember, 1 atmosphere, which is a normal pressure, is 760 millimeters of mercury. So it's definitely reasonable. And we'll need the density of water. We'll take it as being 0.9987 grams per centimeter cubed. Now it depends upon temperature, but it's going to be pretty close. So we know that the pressure exerted by the column of water has to be the same as the pressure exerted by the column of mercury, because they're both exposed to the atmosphere. So we can say dGH for water is equal to dGH for mercury, and because G is the same on both sides, it cancels. What we want to know is H for water, this right here. So we divide both sides by the density of water, like this, plug in density of mercury, height of the column of mercury, remember it was 764.2 millimeters of mercury, so if we divide by 1,000 we get 0.7642 meters of mercury, and there's the density of water that I gave you up here. Plug these in, we get 10.40 meters, so about 30 feet. That's pretty high.